Everybody, it is Mr. Gustin back in the physics classroom here. We're looking at worksheet 3, problem number 1 in unit 2. This is all about friction and objects on angles. So we're going to start with problem number 1. A 1.5 kilogram box sits at rest on an incline despite a force of 5 newtons pulling it up the ramp. There's a couple things here that I want to jot down based on what I see here. At rest means two things. It means its velocity equals 0 meters per second. It means the acceleration of the object is 0 meters per second squared, which in turn means that the F net in all directions equals 0 newtons. Those are just some things we can automatically off the bat by just seeing at rest on an incline tells us about this system. So let's start with A, draw an FBD. Okay, so we're going to do that. We're going to go ahead and sketch our model. Here is our object at the incline of 15 degrees. All right, well, the first force I know that always exists is gravity. And gravity will always pull objects straight towards the center of the earth. So I'm going to go ahead and draw my force of gravity, pulling the box straight down towards the center of the earth. Now there's this angled surface in the way, and anytime there's an object touching a surface, there is a perpendicular normal force. That's the definition of the word normal, is that it's perpendicular to a surface. So there's that. Up the ramp, we have a pull force. We can call it FP, FT for tension, but there's something pulling it up the ramp. And now, despite that it's being pulled up the ramp, there's still a friction force. So, I don't know, my first assumption is that because I'm pulling it up the ramp, there's going to be a friction force the other direction to cancel it out. I don't know how big that friction force is, but there's definitely a static friction force pulling it down, or pulling it in some direction. I think it's down, but I can't be certain. So there's my FBD. We'll talk why we can't be certain in a minute. Let's look at question B. Calculate the magnitude of the friction force. Well, in order to calculate the magnitude of the friction force, I'm going to need a few things. I'm going to need to figure out all of the forces that are in the same direction as that friction force. So friction is parallel to the ramp. So I'm going to write an F net for all forces parallel. Remember, parallel is there's no X and Y direction here necessarily, so we have to Cosmo. And as we tilt, we see, oh, these forces are parallel and some forces are perpendicular. So F net perpendicular or parallel is 0 newtons. How do I know it's 0 newtons? Because there's no acceleration. Why? Because it's at rest. It's at a constant velocity of 0. Let's start taking into account the forces that are in this parallel direction. Let's see here. The first force I see in the parallel direction is the pull force of 5 newtons. So I'm going to say there's a pull force. I'm going to subtract my friction force because that is in the opposite direction as the pull force. And it's static friction because it is not moving. And I have to ask myself, are there any other forces that might be pulling this down the ramp or pushing it up the ramp or pulling it up the ramp? And the answer is yes. It's not initially apparent, but there is definitely a component of gravity that is pulling it parallel to the ramp. We call that FG parallel. And it's down the ramp. So I'm going to make sure it's negative as well, or I'm subtracting it as well because it is in the same direction as that force of friction. At least I think it is. Okay? Let's start plugging some things in. So 0 newtons equals the 5 Newton pull force minus the force of friction static minus Fg is mg, but it's not the force of friction, it's the force of friction parallel. This is going to have to be cosine theta. That component is cosine of the 15 degrees. Let's keep working through our algebra. 5 newtons minus the force of friction static minus 1.5 kilograms, 9.8 meters per second squared, cosine of 15 degrees. I end up equals 0 newtons. What I end up with, I'll grab my calculator, you grab yours, you do a little algebra, I'm going to jump right to the solution. Let's go. One. I end up, when I do my algebra, I end up with the force of friction being equal to negative 9.2 newtons. Negative 9.2 newtons. That means something, right? Should force of friction be negative? That's weird to me. Where did the negative come from? Well, the negative came from us saying that force of friction was down the ramp. By us saying that, we were predicting its direction. When the answer comes out as a negative number, what we say to ourselves is, oh, so it's in the opposite direction we thought it was in. When the answer comes out negative, what that tells us is that we guessed wrong. We guessed wrong. The force of friction isn't down the ramp. The force of friction is actually also up the ramp. And if we went ahead and changed that, up the ramp, up the ramp, up the ramp, now we see our force of static friction is 9.2 newtons. Determine the direction of the friction force, up the ramp. So again, the process for the remaining problems is going to be very similar. You're going to start with a force model or a free body diagram. You're going to write an F net expression for the direction of the forces that you're looking for. And you're going to start plugging in numbers that you're given in order to find either a friction force, a net force, a normal force, those types of things. Okay? Good luck in the rest of worksheet 3, and I'll see you back in class on Monday. See ya!